Good afternoon, everybody. I have notes for you. Wednesday. So Wednesday is Undergrad Research Day. I understand many of you, some of you are also presenting there. I'm going to be in Tahlequah in the morning. I am going to endeavor to be back here for 2 o'clock. So we will hold our normal schedule. If you can be here, great. If you can't be here, that's sad, but also understandable. It is highly likely that I will be running in like from the parking lot to this space to make it in time. So Wednesday might be just a little bit delayed, but I will be here. Let's keep talking about alpha carbon chemistry. I left off talking about how to turn enols into, or ketones into enol forms. I want to show you one reaction where that happens. This is the alpha halogenation of aldehydes and ketones. Or as I like to call it, stuff that's totally on the MCAT. Probably not, maybe it is, I don't know. Alpha halogenation, this is going to be particularly for aldehydes and ketones. So, alpha halogenation means we're going to add a halogen at the alpha position. So where is that? There's a halogen, Br2. Where's my alpha position? One of these guys, right? Both of those technically are alpha carbons, but I need a proton nearby to form an enol. This is going to go through an enol intermediate, and I'll show you that in a second. So we're going to add a bromine at that position, the alpha carbon. There. So alpha halogenation. This is acid catalyzed, and the acid we'll see most often is this guy, known as acetic acid. Well, hey there, half the class. Good to see you guys. Everybody was like waiting in the parking lot, and they're like, no, go. That's how I think about with Zoom meetings. You know how like if a Zoom meeting starts at like 12, the room's like totally empty, and then 11:59, 30 people dump into it. If we met like that in real life, like you're waiting for an interview and then like everyone runs in the room in the minute left, that'd be really disconcerting. Which reminds me of the mechanism for the alpha halogenation reaction. Acidic mechanism was the first step. Protonate what? Protonate everything. Protonate the carbonyl. Carbonyl is going to take a proton. Yes, in this one instance, I am going to make a negative charge here. I'm not going to draw it, so don't mess with you guys' perception of reality, but it does make a negative charge. Now I have my activated carbonyl. We're going to remove a proton from this. I'll use acetate since I just made it. I said I wasn't going to draw it, and here I did. Here I go. Negative charge in the oxygen takes that proton. If you wanted to just write generic base here as well, that's totally fine. Carbon, hydrogen, sorry, I'm moving too fast. What happens next? Base takes a proton. Yeah, make an alkene. So break the carbon-hydrogen bond to make an alkene. That's going to put too many electrons on this carbon. Push the double bond up to the oxygen. What did I just make? Bless you. An enol. No. An alkene alcohol. Okay, so this is now my nucleophile. I've got an oxygen with lone pairs that's electronically connected to this alpha carbon. So now we're going to give it something to shoot at. Sorry, I'm using this reference. Let me explain what I mean by shoot at. I am not a gun person. My wife works with firearms, and so you're gonna hear me call them firearms because I'm that nerdy person of like a firearm is blah, blah. I think of these kind of like guns. Enols and enolates are like firearms to me. The way I understand a gun to work, not that I have one, is that in order to actually make it go pew pew, you have to pull the hammer back or cock it or something, and then you pull the trigger. What we're doing with our ketone is we're taking the uncocked gun, we are cocking it back. So we're giving this oxygen the electron density. So we are turning a non-nucleophilic molecule into a nucleophilic molecule, and then we're going to give it something to shoot at. Each one of these cases, we're going to make an enol or enolate, cock the gun, then we're going to give it give it some sort of electrophile to shoot at. The ketone or aldehyde itself is not nucleophilic. Enols and enolates are nucleophilic. So we form the nucleophile, pull the trigger, electrons flow down from the hammer, out from the barrel, and shoot our electrophile. The carbonyl is acting like a thing that can be turned into a nucleophile, but is not a nucleophile presently. So I think the correct answer is, to this question is all the time. Of when is a gun dangerous? You would say all the time. When is a gun especially dangerous? When it has a bullet in it and it's actually cocked back, right? Because at any time it can fire at that point. This is not going to attack anything. It is in a dormant state. Whenever we take a proton away from it and we turn it into this enol, it is now in a nucleophilic state. So now it can react with an electrophile, but it has to form this molecule first. That's not my final product. How do I get there? Base. It could be the acetate again, but let's just use generic base to get to our opposite box number. Carbonyl. Make the enol, react the enol with the electrophile. That make sense? You're going to see me do this a lot. We're going to take a carbonyl, we're going to make an enol, or more commonly an enolate. And we're going to give it an electrophile. We're going to change up the nature of what the electrophile is, and that's how we're going to make our new bond. That's really the beauty of this is I take a molecule that we have known carbonyls to be only electrophiles. We only ever attack carbonyls, but now we're turning a carbonyl into something that does the attack. For this one in particular, why might we be interested in making alpha halogenated carbonyls? What cool things can we do with them? Let's say cyclohexanone. I react cyclohexanone with bromine and acetic acid. I will make what? Bromic acid. Oh, I gotta erase every one of these things. There we go. I'm gonna put a bromine where? Yeah, at the alpha position. Can I do anything with that molecule? Yes, I can. No, I can't. Everybody go home. Yeah, if I mix in, say, like a base of some sort, let's do like sodium hydroxide. There's lots of bases that could do this. And I could take a proton from down here. And if I do that, what can I do? I can make a double bond. What kind of double bond did I just make? Alpha beta unsaturated. I just made a conjugated double bond. Do we know any reactions that react with conjugated double bonds? Yes, you do, lots of them, right? Amines, Gilman reagents. End of list right now, but there's a lot more. This is an alpha beta unsaturated carbonyl. So previously when I was bringing those up and I was like, hey, if you have an alpha beta unsaturated carbonyl, you could attack it with an amine. And you were like, I learned that and loved that. I'm going to use that in my life. Now you know how to make the other side of that, right? You know how to take an amine to add to this molecule. Questions? Love it. Yeah, the acetic acid is just to get the bromine on there. So then in a second step, you would use sodium hydroxide. You would not want to mix sodium hydroxide into this main first step. Okay, so you can do this not only with aldehydes and ketones, you can do it with other carboxylic acids and carboxylic acid derivatives, but we got to get a little creative about this because if there's an OH here, we need to watch out. 3 different scientists, this is section 22.4, came up with this, the Hell, Volhard, Zelensky. That's a bunch of last names, so HVZ. The HVZ reaction turns a carboxylic acid into an alpha brominated carboxylic acid. To do that, we're actually going to do this in 2 pieces. First step, we're going to have Br2 and phosphorus tribromide. Of PBr fame. Why this is in black? Let's keep going. And the second step is water. And so why am I doing this in 2 steps versus the other one where I just added Br2 and acid? Carboxylic acids don't form enols very well. Or what we call, they don't enolize. I'll just write don't form enols. That's not how you spell easily. It's not how you spell easily either. Easel. Is that right? Why does that look weird? There. Impact. So what's the deal with this PBr3? What does PBr3 do for us previously? Phosphorus tribromide turns what into what? It has. Welcome back. Turns an alcohol into a PBr turns a Friday into a hot mess. PBr3 turns an alcohol into an alkyl bromide. You guys still don't get my PBr references. You are good people. But you know, never mind. So this goes through an intermediate that has a bromine here and here. So this OH was turned into a Br through PBr3. It turned, just like we can use thionyl chloride to turn an OH into a Cl over here. You can use PBr3 to turn the OH into a Br. This acid bromide can then form an enol. The enol can then alpha halogenate. It's really hard to turn a molecule that has an OH on the end here into an alkene because there's just too much electron density with that oxygen providing resonance back. So we get rid of the oxygen temporarily, and then the second step is a hydrolysis reaction, right? So turn an acid halide back into a carboxylic acid. So that's what this H2O is about, is to get rid of the Br that's on here. I don't need you to know the full mechanism for this, but you can use your imagination for how, I mean, you actually could write this mechanism out. You turn this into a Br, once it's on there, form the enol, enol adds the bromine, and then the rest of this is hydrolysis to take us back to the carboxylic acid. Yeah. Perfect. The HVZ reaction is pretty specific. I want you to be familiar with it for things like the MCAT, because they do ask these like random questions. Yeah. PBr3 is the only addition here. Otherwise, it runs the exact same way from what we just saw. You want me to, you're giving me blank looks. You want me to show you what it looks like? Very briefly, not the full mechanism. This thing gets here. I mean, we'll do it stepwise. So everybody see how that forms. PBr3 turns an OH into a Br. Everyone shake your head yes at me, because you know what I mean by that. Cool. All right. So now that we have that, and the next step is to turn this into an enol. That can happen in water, although you'd probably have a little bit of acid in here. So the next thing that would occur is this thing would turn into an alkene alcohol like that. Then that alkene alcohol would attack a bromine. We put the bromine at that position. That gets us to here. The hydrolysis takes the bromine off to back to the OH. Okay. Good. This is the only reaction I'm going to show you that goes under acidic conditions. Everything else is going to be under basic conditions. So not enols, but enolates. I'll put it on here. This should really be just an addendum to the last thing we talked about. You can think of HVZ as just part of alpha halogenation reactions. Enolates are the main show here, because they're just so much more useful. We can do a lot more with them. When we form an enolate, we need to be careful about if it is reversible or not. So I want this arrow to go forward and not backwards. If you look at your notes for the alpha halogenation reaction I just showed you, I used reversible arrows. We're going to need to be really careful about irreversible versus reversible arrows here. If I want that ketone to turn into an enolate, negative charge, so this is a ketone. This is an enolate, and I want it to do so irreversibly. Should I use a strong base or a weak base here? Strong, super strong. If I use a weak base, then it's going to take a proton from this ketone, turn into the enolate, and the enolate's going to go, you know what? I'll take that proton back. And the base will go, oh, that's fine, because I wasn't very strong to begin with. I want a base to come in here and be like, give me that proton. And when the enolate forms, it goes, I don't want to be like this. Give me the proton back. And the base says, no, because I'm strong and strong people are mean and inconsiderate. The strong base that we're going to use here is called LDA. We need to be really careful that LDA doesn't have any protons in it. So we will also put this in THF, tetrahydrofuran. I don't believe I've brought up LDA in here before, have I? Super strong common base. LDA stands for lithium diisopropyl amide. Now this amide tagline is a bit of a misnomer, because when I tell you amide, hopefully you think carbonyl with a nitrogen next door. Right? That is what I've trained you all to see as an amide. Amide also refers to nitrogens with negative charges. So the way this works is you're going to have a nitrogen with two isopropyl groups coming off of it, two lone pairs and a negative charge. So that is an amide ion. A nitrogen with a negative charge is called an amide as well. I'm sorry, I didn't come up with a rule for that. We should have a different name, but here we are. And there's a lithium counter ion that sits next to it. So lithium diisopropyl amide. This is a super strong base because it's a nitrogen with a negative charge and no resonance to move it. And it's really good at being a base instead of a nucleophile because it has these big isopropyl groups hanging off of it that take up a lot of space. So this is a strong base. But a bad nucleophile. That's why we use it. And you might recall from our conversations from OChem 1, if you were in this class, that all strong nucleophiles can be strong bases, but not all strong bases can be strong nucleophiles. The difference is size. If you're very good at taking protons and you're small, you can also go after nucleophile, or you can also go after nuclei. If you are good at taking protons, but you're big, you can only take protons. The idea is if I'm a base, or let's say I'm a molecule with too much negative charge, you guys are a molecule. If I want to come do an elimination reaction, all I got to do is come up here and pick off Bashar. He's a pretty strong, pretty scrappy dude, but he's on the end, right? So I can get to him pretty easy. If I have to bring this whole system with me, right? So I've got my negative charge, but now I got to bring the whole podium with me. I'm going just after Bashar because I'm not dragging this thing to the middle of all y'all, because you're going to beat me up in the process, right? I'm too bulky to make it in. If it's just me, and I can bobble and weave around in here, I'm going to Rin. Want to know why? Because Rin is a nucleophile. He's got a bunch of positive charge. So if I have a bunch of negative charge, that's the place I want to go to. So I'm attacking. But if I can't make it into the middle of the molecule, if I'm too sterically hindered, I'm going to take a proton from the outside. And so this molecule is dragging the podium with it. It's too big, so it's really good at taking protons, and that's it. You're going to see me use LDA quite a bit for that reason. But this base, being as strong as it is pretty dangerous. The reason we have to use it in THF is it'll spark water when it touches it. It's made with N-butyl lithium. And I think we've talked about N-butyl lithium and the accident that happened at UC Riverside, right? So most of the time when you're working with N-butyl lithium, you're trying to make this thing LDA. And they kind of work in the same fashion. So this is an incredibly strong, very strong base, right? All the exclamation points. So let's only use it when we absolutely have to. Let me show you two cases where you can make enolates where you need to use LDA and where you don't necessarily need to use it. Let's compare acetone . Enolate looks like this. This reaction, I definitely want to use LDA. And THF. This is the enolate of acetone. I didn't show you the mechanism for this, did I? Let's do that real quick. It's not hard. Not SN2. It's taking a proton, right? So what LDA is going to do is pull a proton, electrons flow over, push the electrons onto the oxygen. Double bond forms, negative charge on the oxygen. For acetone, I need to use this super strong base. If I have a dicarbonyl, I don't have to use the strong base. I can get away with using something like ethoxide. And you'll see this almost always with a counter ion, sodium ethoxide, potassium hydroxide, something like that. Ethoxide is nowhere near the same strength of base as LDA, but I can take this proton much more easily. The question I have is why? Why can I use a relatively weak base down here, but I have to use like the earth ending base up top to take that proton? What's the difference between these molecules? Or more importantly, what's the difference between these two enolates? Resonance. This one has resonance, right, between an oxygen and a carbon. This one has resonance between an oxygen and a carbon. Are there any other resonance structures? Yeah, I can push the electron density from this oxygen all the way over to that carbonyl. Electrons pushed down from here, over from there, up to there. So this enolate ion has additional resonance. What do you think that means for this enolate ion? Is it more or less stable than the top enolate ion? This is more stable. The more stable the conjugate base, the stronger or weaker the acid. The stronger the acid. So more stable conjugate base, stronger acid. The pKa of acetone up here. Put it over here so it's coming that way. pKa of acetone is 19. What do you think the pKa of these protons are? Higher or lower than 19? Lower. pKa of those protons are about 9. 10 zeros. What is 10 zeros? 9 zeros is a billion. Yeah, so 10 zeros, 1 trillion, right? No, 10 zeros is 1 with 9 zeros underneath it. A lot. This molecule is a lot more acidic than acetone. Because when I pull one of these protons, the negative charge can resonate back and forth here. The more stable the conjugate base, the stronger the acid. If I have a super strong acid, I do not need a strong base to react with it because I'm so much more acidic here. LDA will produce this enolate ion, but why put yourself in harm's way using this unsafe base when you can just do it with something that's not going to explode? We will talk about these a lot more in chapter 23, because sometimes we want these reactions to form irreversibly, and sometimes we want them to form reversibly. So for now, just put a pin in it, and we'll come back to this idea that different bases can be used to get the job done. But before I leave that part, any questions about making enolates? Yeah. Good question. Why did the base take a middle proton and not one of the protons in the end? They're both alpha. This alpha is special though. It can resonate at all, right? So if I get my double bond here, there's resonance that goes between these. If I take a proton from the end, this is stuck over there. I can't get that charge. That doesn't work, right? I can get that charge to hop across that middle carbon. It's insulated. So these protons in the end have a pKa of 19 as well. Those protons have a pKa of 9. The acidity is hugely different between them. So when the big bad wolf comes knocking on this door, it's taking these piglets, not the ones on the outside. That got weird. It's taking the protons in the middle, not the ones on the outside, right? Because as it walks up, it starts pulling on protons. These protons on the end put up a huge fight. The protons in the middle go easily. Good question. Others? Okay. Let me show you some reactions that kind of follow along these lines. Enolate reactions. We're going to ease into them, and then we'll finish up with 2 reactions that are just a nightmare. But let's start with the easy ones. You're going to see me draw out these carbon-hydrogen bonds a lot to start, and then I'll slowly wean us off of doing this. So the first one I want to show you is, I didn't leave myself a lot of space, alpha halogenation. I know what you're thinking. Dr. Green, you just showed me alpha halogenation. Are you having a stroke? No, I'm going to show it to you using basic conditions. So I showed you alpha halogenation under acidic conditions. Now we're going to do it under basic conditions. The way this is going to work is we're going to add in sodium hydroxide and Br2 at the same time. That is going to ultimately give us a halogen at the alpha position. How's the mechanism for this work? What's the first step? Not a nucleophilic attack. Got a handgun, totally harmless, right? I shouldn't talk about guns. I have a slingshot. I have a slingshot that has no pebble in it. I need to arm the pebble, right? So this isn't a nucleophile. That could be a nucleophile, but it's just going to make an OH-Br bond, and those will fall right apart every time, right? It's a lemon. So an OH is going to turn this into a nucleophile. How do I show that? Gary? Put what is done. Yeah, the OH is going to attack the proton. Yep. Love it. That one in between and then up. Got it. All right, this is going to form reversibly because I'm not using my super strong base. That makes my enolate. All right, now my slingshot is armed. Before it was just laying there with a rock next to it. That's not going to hurt anybody. Now I put the rock into the slingshot and pulled it back. So now I got a dangerous slingshot. At this point, what's going to happen? I set up my, actually, we're just going to go over here now. I set up my Coke cans, making this as non-violent as possible. Aim at my Coke cans, release the pebble. It's going to float out of the slingshot, cross my arm, hit the Coke can. I'm a great shot, apparently. Giving us a bromine at the alpha position. I took a thing which was not a nucleophile. I armed it. I turned it into a nucleophile. Then I shot at some electrophile, in this case Br2. Make sense? Feel like the slingshot reference better? And they just like look like guns to me a little bit. I don't know. There's something about like this, like kind of standing up, and that's kind of like a little barrel. I don't know. I'm going back to the gun thing. I'm on a recording, so I'm not going to say anything about it. Talk to you about it later if you want. So this is alpha halogenation. I want to talk about alkylation next. That's not how you spell alkylation. You guys are good sports, you know that. All right, for alpha halogenation, we need to be a little bit more careful. So we're going to do this in 2 steps. The first step is to add something to turn this into a nucleophile. So again, we'll just use sodium hydroxide. This is a stand-in for base. We're going to use a bunch of different bases. Actually, sodium hydroxide is not preferred here, but we'll come back to that later on. And the second step is we're going to add some sort of alkyl halide. NaOH is going to turn my ketone into an enolate. Enolate is going to shoot at alkyl halide and make what? Not an acid halide. Our group is going to be added to the outside here. Oh my gosh, what did I just make? I just made a new carbon-carbon bond. Oh my God. That's exciting. We better show the mechanism for that. I just said the first step is to make the enolate. I'm really exaggerating these carbon-hydrogen bonds because I really want you to see these anywhere there are protons on an alpha carbon. That is a place you can make a nucleophile now. We're going to do a lot of reactions where you need to recognize these are areas that can be armed. You can take a thing that's not a nucleophile and in one easy step, turn it into a nucleophile, which gives you lots of other options. Let me walk me through this. You've seen it. This is like the fourth time. Love the use of the verbiage here. Take the proton from the alpha carbon, move that over to make a carbon-carbon double bond, take the carbonyl oxygen bond up onto the oxygen. All the big words. Bashar, what'd you just make? You did indeed. What alkyl halide did you wake up with on your heart, Vika? Methyl ethyl propyl butyl. Propyl, yeah. And halogen. Charles, what's the halogen of the day? Propyl chloride, I love it. Should we do one propyl chloride or two propyl chloride? Dealer's choice. Isopropyl, that sounds nice. There's isopropyl chloride. What do next? Shark. What do I do now? Not the chloride attacking the lone pairs. So the lone pairs are going to flow down from the oxygen like that. So my hammer falls, the energy flows through the alpha carbon. Where? Carbon. From here to the carbon. Kicks off the chlorine. Gives us a new bond there. To our alpha alkylated position. Now, since we used isopropyl chloride, we do need to worry about this acting like a base and making an alkene over here, but it's possible for it to be a nucleophilic attack. This nucleophile is kind of big though, so watch out for that. As the nucleophile gets bigger, it tends to act like a base, and we lose things that way. Technically, this type of alkylation is called an alpha alkylation. There's many types of alkylations, but we put an alkyl group in green at the alpha position here. You guys seeing the theme to this? Take carbonyl, remove proton from carbonyl, make enolate. Enolate then attacks something. We're going to change up what that something is. So we're going to just do this over and over. We take a carbonyl, remove a proton, arm it, and then attack something else. Questions about adding a bromine or an alkyl group? Yeah. If you had done like a methyl, like methyl iodide, yep, then you'd have just a CH3 over here. Let's just do it. That bond would attack the carbon, pick off the iodine, and you'd have a CH3 over here. Oh, no, you wouldn't. Just kidding. We'd go there. Watch out for that. The mistake I almost just made was I almost dropped a carbon. When you make new carbon-carbon bonds, that's a great time to lose count of your carbons. Especially when you run this next reaction that you guys are gonna hate. I'm going to show you two reactions that have big long names and they have big scary reagents, but they're actually not that complicated. And once you get the gist of it down, I think it'll flow a little bit more naturally. But prepare to be mad at me. Prepare to be more mad at me than you are right now. I'm going to show 4 minutes, 10 minutes. I wasn't, but now, yes, I am. Challenge accepted. The first one is the malonic ester synthesis. You see Charles trying to kill my class early? Yeah. Yes. I don't know. I don't have any section numbers after this. I have a feeling that we've moved on. But it's probably in section 22.6. I have a feeling section 22.6 is huge. So, yeah. The malonic ester synthesis has a bunch of scary reagents, but what it does is it turns an alkyl halide into that same carbon that now has, oh, shouldn't have used blue down here. Let's stick with it. A CH2 and a carboxylic acid attached to it. So my malonic ester synthesis is going to add what's in blue here. Malonic ester synthesis, MES. Okay, the reagents I'm going to show you are the part that's going to freak you out. But overall, what's going to happen is I'm going to add to whatever is attached to my alkyl halide 2 carbons, one of which has a carboxylic acid. What is that? I'm sorry. In blue, what's this piece? Acetic acid. The malonic ester synthesis makes acetic acid derivatives. I'm going to show you. It starts with a thing called malonic ester. Okay, so the malonic ester synthesis uses this guy. This is called diethyl propane dioate. ET is what? Ethyl, diethyl propane dioate. I think I told you about that molecular biologist and biologist renamed all of our molecules. We came up with great names for them, and they renamed all of them with some common name. This one is called malonic ester. That's why this one's called the malonic ester synthesis, because we start with malonic ester. And then what we're going to do is first add a base to this. So that's ethoxide. I'll go ahead and I'm just going to draw this out. Ooh, no, not in blue. Ethoxide is going to do what to malonic ester? Take a proton here from the middle. And keep in mind that this is also ethoxide, right? So ethyl O minus. If that attacked my ester and kicked this off, I would make the exact same thing. I'm just swapping out one base for the next, which is why you're going to see me use this base paired up with whatever's on the ester here. Ethoxy, ethoxy. This O minus is going to take a proton, push the electrons onto the carbonyl. That's going to form an enolate. Then I'm going to feed my enolate something to shoot at. Say butyl bromide, 1 butyl bromide. What's the reaction between these two look like? The O minus is going to push down. So I know this is a lot more complicated looking because it's got other stuff going on, but this is an enolate. Notice this is a dicarbonyl. So this is a irreversible arrow. I don't need a super strong base to take a proton from this. My relatively weak base can irreversibly form that enolate for me. So the electrons are going to flow down from the oxygen, over from the carbonyl, or from the alpha carbon, attack the carbon bearing the leaving group, take it off. Oops. Why did I draw this in blue? I'm not sure. Do I regret it? Yes, I do. Does it need to be in blue? Has it been a long day where I'm going to start asking my own questions and answering them? Yes, it is. I have added 1, 2, 3, 4 carbons on here. So 1, 2, 3, 4 carbons off of there. And then from here, what I can do is finish this reaction with H3O plus and heat. No, this does not form a tetrahedral immediate. I would have done my little song and dance if it was. This is going to do some crazy stuff that I'll show you here in just a second, where it's going to hydrolyze the ester into a carboxylic acid. I'm going to leave this all curled up on itself just so you can see where it comes from. 1, 2, 3, 4 carbons coming off of this, but there is no other carbonyl over here. So this is my acetic acid derivative with 1, 2. Now this looks really dumb, doesn't it? Make it look kind of. I'm gonna make it look zigzag. 1, 2, 3, 4. That's my carboxylic acid derivative. That's the alkyl group that I added onto it. The hydronium kicked off. Well, I don't want to spoil it. We'll get to it about what happened to the other piece. But if you're wondering, hey, there was another piece of this and it's gone, you're right. Hold, please. Before I show you where that other one went, this is a dicarbonyl. There is still a proton here. So guess what? I can do it again if I want to. And you know that I do. So I could finish the reaction here, or I could run another set of reactions where I turn this again into an enolate, take the proton from that, make the enolate there, and then give it something to attack, let's say methyl iodide. Which would then give me 2 different alkyl groups on there. A CH3 and a 1, 2, 3, 4 carbon unit come off of there. Does everybody see where I got this methyl group from? I just took that proton with a base, made an enolate. Enolate attacked another carbon, kicked that off. Now we're back here. Same process I did to get to here, just repeat it again. Finish this off with H3O plus and heat. And now I have 2 different things hanging off my acetic acid. One of them is a methyl group, and the other one is 1, 2, 3, 4 carbons. This is just 2 different pathways we can take. As many protons as there are, that's as many times as I can turn this into an enolate. 2 protons, 2 nucleophiles. Now I only have 45 seconds to tell you where the carbonyl goes. So I'm going to have to leave you in suspense. Because if I show you the decarboxylation right now, your heads are going to literally explode more than they already are. So hold tight on what happens to this other carbonyl. We will pick up with that first thing on Wednesday. Have a good one. What?